welcome to the course of Electric Machine 1, lecture number 3. So we start with some more basic hysteresis loop. Transformer and most electric motor operate on alternating current. In such devices, the flux in the iron changes continuously both in value and direction. The magnetic domain are therefore oriented first in one direction, then the other, at a rate that depends upon the frequency. Thus, if the flux has a frequency of 60 Hz, the domain describes a complete cycle every 1/60 of a second, passing successfully through peak flux density, that is B maximum positive, and density minus Bm, that is on the negative side, as the peak magnetic field intensity alternate between Hm positive side and minus Hm on the negative side. If we plot the flux density B as a function of H, that is the magnetic field strength, we obtain a closed curve called hysteresis loop. We study hysteresis loop because there is a hysteresis losses in the DC generator, AC generator and transformers. So in this loop, basically we study that alternating current produce flux which change in the iron core in a transformer, in a armature iron core in machines continuously from positive to negative and from negative to positive, and also its direction changes. Thus the magnetic domain are therefore first in one direction, then in the opposite direction, and it depends upon the frequency, that is 50 Hz or 60 Hz. So this is the hysteresis loop, starting from 0 and goes toward the positive maximum. Then this is A, then come towards B, C, D, that is negative Bm and negative Hm, then E, C and A. So we study hysteresis loop. On the basis of this, we are going to understand hysteresis losses. The magnetic material absorbs energy during each cycle, and this energy is dissipated as heat. Magnetic material means the iron core in the transformer or in machine. The iron is used as an armature. So hysteresis losses are also produced when a piece of iron rotates in a constant magnetic field, as we are going to study in generators in this course, that is DC motor or DC generator. So hysteresis losses produced when a piece of iron rotates in a constant magnetic field, as shown in this figure. We have a north pole and a south pole, and this iron rotates in this field. We have south and north pole under the north pole and south and north pole under the S pole. In a second rotation, the armature magnetic field changes, that is it's change from north to S, south, and from south to north. So in this way, the magnetic material absorbs energy, and this energy is dissipated as heat, and due to this we have losses, which is we denoted from hysteresis losses. The second one is another losses in the machine. We will going to study it also, that is eddy current losses. The eddy current problem become particularly important when iron has to carry an AC flux. This is the case in all AC motors and transformers. We can reduce the losses by splitting the core along its length and insulate each section from one another. That is, we laminate the core, and in this way we reduce the eddy current losses. The core of AC motor and generator are therefore always laminated. A thin coating of insulation covers each lamination to prevent electrical contact between them, and we insulate each eliminated sheet from one another. Now we come to the DC generator. First of all, we are going to study DC generator in this course. We come across in depth and in detail the basics that are very important for students to understand and learn in order to get a grip on DC generator and motor we are going to study in the upcoming lectures. So first, DC generators, direct current generators. DC generators and motors are built the same way. Therefore, any DC generator can operate as a motor and vice versa. Being DC generator and motors are built in a similar way, therefore we can operate this machine as a generator as well as in the form of motor. Due to their similar construction, the fundamental properties of generators and motors are identical. Thus, anything we learn about the DC generator can be directly applied to DC motors. So we begin our study with the basic principle of two-pole generator when it operated no load. How the voltage is generated and what determines its magnitude. After this, we are going to study the behavior of generator under load and its mechanical torque, direction of current flows, and importance of armature reactions. So we will use and utilize all the basic we have studied so far. First of all, we have generating and alternating voltage. We have already studied what is alternating voltage. Now we are going to see how it is generated in the generators. The voltage generated in any DC generator is alternating and only become DC after it has been rectified by the commutators. In each and every generator we studied in electrical, like DC generator, DC generator, AC generator that we call alternator. They are produced in alternating voltage. As we are studying DC, we convert it into DC voltage by the help of a commutator. Commutator acts as a rectifier. Rectifier is a device which converts AC voltage into a DC voltage. This is the figure, the basic two-pole generator. We have a north pole, a south pole, a coil, simple loop coil, revolving in magnetic field which will going to cut the flux, and EMF will be induced in this coil. This is connected to the slip rings, and these are X and Y, the carbon brushes. They take the load to the external load. So figure show in elementary AC generator composed of a coil that revolve at a 60 revolution per minute between the north and south pole of a permanent magnet. The rotation is due to an external driving force such as motor, not shown in figure for simplicity. The coil is connected to two slip rings mounted on the shaft. The slip rings are connected to an external load by means of two stationary brushes X and Y. So in a generator, in a basic generator, we have two main parts. There is the magnetic field, this one shown with the help of a permanent magnet, and a coil that is rotating in this field. So these stationary part we call stators of the generators, and this rotating part we call it a rotor of the generators. As the coil rotates, a voltage is induced. This is the equation of the induced voltage. B flux, I is the current, and V, BIV. We already studied this equation between its terminal A and D. As the coil rotates, a voltage is induced between the terminal A and D. This is the terminal A and this is the terminal D. This voltage appears between the brushes and therefore across the load. The voltage is generated because the conductor of the coil cut across the flux produced by the north and south pole. As we already studied, when a conductor moves in a magnetic field, a EMF is induced in the conductor, or in this case in the coil. The induced voltage is therefore maximum 20 volt in this scenario, say when the coil is temporarily in the horizontal position. No flux is cut when the coil is in the vertical position. Consequently, the voltage at this instant is zero. Another feature of the voltage is that its polarity changes every time the coil makes half a turn. So, in short, there is a coil that is rotating in this magnetic field. This magnetic field produces flux. The coil cut the flux, and its rotation causes a changing flux in the coil that is linked with it, and EMF is induced in this coil, and with the help of this, a current flow in the coil that come out of this generator, and if there is any load, it will provide it. This is the generated EMF, that is its maximum point is plus 20 volt, negative is minus 20, and it is alternating in nature. Its direction change after every half cycle. There is positive side and negative side, as we already discussed in alternating voltage or AC voltage that we have studied. Now we coming towards the direct current generators. A commutator in its simplest form is composed of a slip ring that is cut in half, with each segment insulated from the other as well as from the shaft. One segment is connected to coil end A and the other to coil end D. We started the DC generator and studied that alternating voltage is produced in the coil. So how we convert it into DC generator, or how we convert the AC voltage to DC voltage. We use a commutator. Commutator is a slip ring that is cut in half in between two parts, and each part is insulated from each other as well as from the shaft on which it is mounted. One side of it is connected sorry, to the coil in A, and the other to coil in D. The commutator revolves with the coil, and the voltage between the segment is picked up by two stationary brushes X and Y. The voltage between brushes X and Y pulsate but never change polarity. Alternating voltage in the coil is rectified by the commutator. This is the pulsating voltage. We call it DC voltage because it not change its polarity, mean it is on the positive side. We can convert it into pure DC by different techniques. This is we call a DC generator which have a commutator which converts the AC voltage generated in this coil into DC, and the load got DC voltage. This is the commutator that is split into two pieces, is shown in the figure, and insulated. This piece is insulated from the lower piece, and also from the shaft it is connected. Now, what is the difference between AC and DC generators? It is simple. We studied that a coil, in coil a voltage is produced that is AC alternating in nature, and we in DC generator convert it with the help of commutator. So there is one main difference. In AC generator we don't have commutator, and in DC we use commutator in order to convert AC voltage into DC voltage. So the machine only differ in the way the coil are connected to the external circuit. AC generator carries slip rings, while DC generator require a commutator. We sometimes build a small machine which carry both slip ring and a commutator. Such a machine can function simultaneously as AC and DC generators. Now, neutral zone. Neutral zone are those places on the surface of the armature. Now, what is armature? The armature, that is the rotating part in the generator that are shown. So neutral zone are those places on the surface of the armature where the flux density is zero, means there is no flux. There are places on the armature where there is no flux density, means zero flux, and the generator operated at no load. The neutral zone are located exactly between the poles. No voltage is induced in a coil that cuts through the neutral zone. We always try to set the brushes so they are in contact with the coil that are temporarily in a neutral zone. We connect the brushes in this zone in order to minimize the sparking effect that is produced in the generators. Now, generator under load. We will study generator under no load situation to build a grip on the topic. Now we going to towards the advancement. So generator under load. Consider, for example, a two-pole generator that is driven counterclockwise, mean in anti-clockwise, while delivering current I to a load. Mean we have a two-pole generator that is driven in anti-clockwise direction and give current to a load. The current delivered by generator also flow through all the armature conductor. Referring to the figure, this one, the armature conductor under the S pole carry current that flow into the page away from the reader, and the armature current under the north pole flow out of the page towards the reader. This is a simple two-pole generator, north and S pole. This is the armature or the rotor part that rotate in this magnetic field, and this is the load connected with this generators. In the north, under the north pole, these are the conductor of the armature, and this is the conductor of the armature under the south poles. So the dot and plus show the direction of current away from reader or towards the reader. Mean under the north pole, the conductor of the armature have current in one direction, and under the south pole, the armature conductor have current in the opposite directions. Because the conductor lie in a magnetic field, the armature conductor or the rotor conductor, they are subjected to a force. As we already studied that a current carrying conductor when placed in a magnetic field, it experiences a force. If we examine the direction of current flow and the direction of flux, we find that the individual force F on the conductor all act clockwise. We studied that this generator is rotating in the anti-clockwise direction, and we find that the individual force on the conductor acts in clockwise direction, opposite to the direction the torque is produced. In effect, they produce a torque that acts opposite to the direction in which the generator is being driven. To keep the generator going, mean in running condition, we must exert a torque on a shaft to overcome this opposing electromagnetic torque. The resulting mechanical power is converted into electrical power, which is delivered to the generator load. Thank you for today's lecture.